Thanks, Mia, and welcome everybody to yet another episode of the Smart Technical Webinar Series. Special welcome to our speaker, Dan O'Malley from Los Alamos National Labs. Dan is a scientist in the Computational Earth Science Group. He holds a PhD in applied math, and he also has degrees in computer science and mathematics, all from Purdue. His research interests are in computational science, particularly for subsurface flow and transport applications, in addition to quantum computing and machine learning. He's won a lot of distinguished awards, far too many for me to list here, but they're all in his bio as part of the meeting invite. And more to the point, Dan has been a member of the Smart Phase 1 technical team. Today, he's going to talk about differentiable programming, bridging the gap between numerical models and machine learning models. So on the one hand, we have physics-based models, which solve partial differential equations using numerical techniques or analytical, semi-analytical techniques. And then using machine learning, we can also come up with simply input-output models that don't have any underlying causal mechanisms. But we're always trying to look for bridging techniques such as physics-informed neural networks and more recently, differentiable programming. And that's the limit of what I know about the topic. So I'm looking forward to Dan's talk and learning more about it. So the floor is yours, Dan.
Thanks so much, Rikanta, and thanks for having me, giving me the opportunity to come here and tell you all a little bit about my research. And yeah, so as you mentioned, I'm going to be talking today about differentiable programming, which is sort of one way to bridge the gap between these numerical models and machine learning models. And so if you're looking at the slide, you can see a picture of a bunch of people in a room, and these people are all doing computations. And so part of the reason why I'm so excited about differentiable programming is sort of, if you think about like in the early days of computing, like before we had computers like we had now, these people in this picture, they were called computers. And like the power of a computer is that it can replace this room full of people doing calculations with just a machine that can do, much faster calculations, much more reliably. And, it's just sort of, it's better to have a chip that can do 1 billion things every second than to have a room full of people doing stuff. And so the idea for differentiable programming is similar to this. So, now we don't really have rooms full of people doing calculations like that, but it is, we now have rooms full of people writing code. And so like the idea for differentiable programming is that you can really reduce the amount of code that you need to write. So you don't necessarily need rooms full of people writing code. You can have the computer write a lot of the code for you and sort of allow us to, break codes faster, write codes better. And so that's kind of some high level idea why this is exciting to me, at least. And so just before I get started, I want to thank, some collaborators. So a lot of people participated in different aspects of this work. So this is sort of in order of appearance. So Dylan Harper used to be at Lannells now is at the Freshwater Trust. There's a grad student I work with at MIT, Scott Hansen, who's a professor at Ben Gurion, University of the Negev. And then a few Lannell people, who's a postdoc working with me, and John Golden, who's a former postdoc, who's now a staff member here at Lannell. Monty Selenov used to be a staff member here, now went off and started his own company. Bi-Chang Yan, who used to be a postdoc here and now is at KAUST, and then Rajesh Pawar, who's probably well known to a lot of smart people. Alex Pachelieva, who is also a postdoc here, and Hari Viswanathan, who probably is also pretty well known in the smart world. And so all the codes I'm going to be talking about are open source. The two main codes will be this code called DPFEHM, which is sort of maybe a successor to Lannell's long-running code called FEHM, and the basic idea is to add differentiable programming to the basic capabilities of FEHM. The other one is nonlinear equations .jl, and this is a code that does a lot of the automatic differentiation that's at the core of these differentiable programming ideas. So they're on GitHub, they're open source. If you're a Julia user, you can, for instance, install dpfbhm by just doing import pkg and then pkg.add dpfbhm. And of course, I know that probably most people are not Julia users, and it's much more common for people to be using Python tools. I think especially PyTorch seems to be one of the most popular tools around. And so you can still use all this stuff within PyTorch. So me and Javier, who's here today, and a guy at Landell named Nick Lubbers, we put together this package called Julia to PyTorch, which basically lets you integrate differentiable Julia codes within PyTorch models. So you can use all this stuff within PyTorch if you want to. And then so just a bit more background about like what differentiable programming is. So differentiable programming is basically a buzzword, and it sort of has different names. So sometimes it's also called software 2.0. And if you're more familiar with the concept of automatic differentiation, which is sort of at the heart of all these machine learning frameworks, you can think of differentiable programming as automatic differentiation writ large. And the basic idea is that traditionally, like machine learning frameworks have been really good at differentiating things like neural networks that are sort of have a relatively simple computational structure. And the idea for differentiable programming, the long-term goal of differentiable programming is to just let somebody write, any code they want, and then have the computer be able to automatically differentiate that code. So like to be able to compute the gradient of some function or the Jacobian of a function or higher order derivatives like the Hessian and things like that. And so, this idea is sort of exciting to people, not just in science, but also coming from just the machine learning world. So there's this tweet by Andrej Karpathy, who is, he's like the machine learning head honcho at Tesla. And so he has this tweet that says, gradient descent can write better code than you. I'm sorry. And he has this accompanying blog post that he goes into a little more detail about sort of what he's thinking. If you can see my mouse, it's quite small, but he has this diagram sort of in the lower left-hand corner where like there's this circle, and in the middle of the circle, there's this, sort of as you go farther out from the middle of the circle, you have this, concept of program complexity. And he sort of the idea is that like with software 1.0, which is sort of like somebody sitting down and just writing code by hand, you're sort of limited in how complex the programs can be. But with software 2.0, where you can differentiate the programs and optimize them and train them and do things like that, you can end up writing you can create computer programs that do much more complex things. So like Andrej Karpathy at Tesla is sort of probably thinking about things like writing a computer code that drives a car. So like you can imagine that it would be extremely difficult to sit down by hand and try to code out like all the rules you would need to know in order to like safely drive a car. So that sort of seems like maybe impossible. More possible is using the software 2.0 approach, where you're sort of writing some code that you can then train. You have maybe some complex machine learning model like a neural network or a transformer or whatever, and you sort of train that, and that at least seems plausible that you could use it to track a car. Like another example that people probably have seen a lot of recently is there's recently these sort of text to image machine learning models have become really popular, and they're super cool. So like you can basically say like, show me a picture of a panda riding a skateboard in Central Park, and it'll like create a picture of that. The machine learning model will do that. So you can imagine that writing a computer program by hand to do that would be like almost impossible. To be able to take any text and create a picture of that. But with this sort of software 2.0 approach, where you train the codes, this is possible. And then sort of moving into the upper right corner, there's this post by Jan LeCun, who's sort of like the head honcho machine learning guy at Facebook. And he starts out sort of a little bit tongue-in-cheek, and he says, okay, deep learning has outlived its usefulness as a buzz phrase. Deep learning is dead. Long live differentiable programming. And then sort of the post goes on, and it's a little more serious, and he gets into why some of these ideas are exciting. And he says that people are now actively working on compilers for imperative differentiable programming language. this is a very exciting avenue for the development of learning-based AI. And so one example of this is the people at Julia Computing at MIT who have been creating this Julia programming language. They've basically been trying to create one of these imperative differentiable programming languages that he's talking about. And just to give an example of the kind of thing they're trying to enable is like, if you look at this picture, they have a neural network that's being fed into an ODE solver. And so it's very hard to see, but this is a little picture of a trebuchet here launching a projectile and trying to hit a target. And so they're training this neural network to, get the trebuchet to be able to hit a target, given some information about like how the wind is blowing and where the target is. And then the neural network has to sort of tell you how to operate the trebuchet. And, it's minimizing some loss function. And you could imagine that, again, it would be hard to like write a computer program that sort of operates this trebuchet given some wind and target information. But it's relatively easy to just write a computer code that like says how the trebuchet works, and then you connect that to a neural network, and then you can train those things. And you sort of have an easy way to like operate this trebuchet given the wind targets or the wind speed and the target location. And so like this is a very simple toy example that's just kind of cute. And a lot of my talk is kind of going to be about doing this for like, more complex systems, like, in particular, like for subsurface systems, combining these machine learning ideas with physics models of, for instance, like flow in the subsurface and, seeing if we can, expand these ideas to sort of the more complex physics that we're interested in. And then just to go into like comparing a little bit about like machine learning and sort of what's happening in the inverse modeling world. So like when machine learning started becoming very popular, some of the people I know in the inverse modeling world were like kind of upset about machine learning because they just sort of felt like, well, like machine learning, like we already do all the stuff that they do. So like what's new and interesting here? Like why is all the funding going to these machine learning people when we already do everything they do? And so like, but the reality that came out of that for me was that like there's actually a lot in common between these two fields. So like for instance, if you're doing inverse modeling or machine learning, you're both things are minimizing something. We have like somewhat different jargons for the things where you talk about what we minimize in machine learning. People usually talk about minimizing a loss function. In inverse modeling, it also varies from field to field, but you might think of it as minimizing some data misfit, how bad the model is misfitting the observations plus some regularization to make the problem more well posed. The thing that's very different between the two is the model structure is very different. So like in machine learning, you have a neural network. In inverse modeling, we usually have some partial differential equation solver. They're both using gradient-based optimization methods. In the machine learning world, they're using like backpropagation to differentiate these neural networks. And traditionally, in the partial differential equation world, adjoint methods have been like the efficient way to do this. Oftentimes they both have lots and lots of parameters to optimize. You see these machine learning models now with like hundreds of billions of parameters. And in the subsurface, we also have lots and lots of parameters because oftentimes we want to know like what is the heterogeneity of the subsurface, and that generally means we have like a parameter at every point in space on our mesh. So like the number of parameters is going to be proportional to the number of mesh nodes. And what comes out of the optimization for the machine learning people is neural network weights. And for the inverse modeling world, it's like physical parameters. So like, for instance, in subsurface flow, it might be permeability. If you're doing seismic, it might be some velocity. But I guess like the key thing is that like one of the, they've done this, they computed the gradient with this back propagation method traditionally in machine learning, and we've been computing gradients using adjoint methods in physics modeling. But differentiable programming is something that generalizes both of those methods. So basically, the same tools that do this differentiable programming can sort of automatically do this back propagation in that people use in machine learning, and they can automatically do these adjoint methods that we use in inverse modeling. So like these two fields already have a lot in common, and differentiable programming makes them have more in common. So I think that's good because then we can sort of leverage things that are being developed in each of these fields. All right, so probably not in the smart crowd, but there's still people I run into pretty commonly who don't like machine learning. And so if you don't like machine learning, I think you should still care about differentiable programming. And the reason why is that so differentiable programming can really accelerate the time it takes to compute a gradient. So this plot you can think of as so this is the time to compute the gradient as a function of the number of nodes on our mesh. And so this blue line you could think of as being how long it takes to compute this gradient using DPFEHM, and the red line you can think of how long it would be to compute the gradient using LANL's existing simulator called FEHM. And so it dramatically accelerates this. And so this is for a nonlinear model. Basically, if you're doing this with FEHM, you have to run the model once for every parameter you have. So if you have parameters for each grid node, that means you have to run the model a lot of times. Whereas with differentiable programming, you basically just have to run the model twice, no matter how many grid nodes you have. And so that's where the speed up comes here. And so yeah, even if you don't like machine learning, you should still be interested in differentiable programming because it can really just accelerate these things that are at the core of traditional model analysis workflows like inverse analysis and uncertainty quantification. If you really like machine learning, I think you should also be interested in differentiable programming. So the thing that's really nice here is you can combine rigorous, trustworthy physics models with machine learning models, and you can kind of connect them just like Legos, and the differentiation sort of just works. So on the left here, you have some code that's showing, I guess you could think of it as a neural network model. So this is just a model with 3 layers, basically. So this is a dense neural network layer. This is a physics model. So this is, an example on the left of showing what kind of physics you can put in here. So this is showing a Richards equation simulation where you have some fluid coming in from the top of the domain. There's a low permeability region here, and you get some pressure buildup over this region. And then there's some gravity-driven flow over the edge of that region. And so you can have this trustworthy physics that's backed up by decades of research in how to solve these partial differential equations. You can just put that in the middle of your machine learning model, and then you can train it just in the same way that you would for any old machine learning model. So I think that's kind of powerful to be able to really have this trustworthy physics in there. And so if you like machine learning, I think this is good. And of course, the other thing that's really nice about machine learning is it's so easy to build the models. And you can sort of build the models easily using this approach too. So there's a question which is, my understanding was backpropagation in neural networks is based in the adjoint method. Would you please clarify? Yeah, I mean, they're basically the same thing. So I would say the general thing is just reverse mode automatic differentiation. So they're both special cases of this. So yeah, they're sort of 2 instances of the same thing. They were discovered independently in 2 different fields and given 2 different names, but yeah, they're basically the same thing. And so that's why this differentiable programming idea can generalize them both. And also, if you're just very busy and you don't like to write code, I think this is also a powerful idea because it writes a lot of the code for you, and I'll go into a little more detail about that later. So this is showing on the left, this is something like 20 lines of code, a little less than 20 lines of code, I guess. And so this is a Richards equation simulator. And basically this 20 lines of code is just describing the Richards equations. And then the computer is automatically looking at this code and figuring out how to compute Jacobians and things like that you would need to solve the equations. And so it writes most of the code for you. And so if you're busy or lazy, that's also good. All right, so what's the basic mechanisms for how this works? Let me just walk you through a really simple example. So this is the simplest subsurface flow problem I could think of. Suppose you wanted to solve these equations for H. And so if you look at this, you can see that it's a diffusion equation. So you can think of H as the pressure or the head. And basically we have constant permeability, and these Q's are some fluid source or sink. And again, like this is a super simple problem. It's completely trivial, but I just want to use this simple example to illustrate, how this method works. So again, here we have the equations. If you wanted to describe these equations using this framework, you just have to write a few lines of code. So you have this function, which I call GW1D. It takes two inputs, H and Q. So these are like the components of the equation. And the first thing you do is you sort of say how many equations there are going to be. And in this case, there's just 3 equations. So we put 3 in here. And then we can, so like the way that I think of it is that it's sort of, you start out with 3 equations and the equations are like 0 equals 0. And then as you go through the code, you're adding terms to the equation. So this is saying add a term to the first equation. And that term is -2 times H1 plus H2 plus Q1, which is just, the same as this right here. And then you, so now basically we've represented this first equation. And then you do the same thing for the second equation and the third equation. So add a term to equation 2. The term is H1, that's this term, -2H2, that's here, plus H3, that's here, and plus Q2, that's here. And the same for the third. So like basically the code you write is just, the job of the code you write is just to describe these equations. And then there's this funny thing here at the beginning of the code that says at nonlinear equations, dot equations. And that's like the thing that tells this package of nonlinear equations that it should look at this code and manipulate it and write a bunch more code. So again, like this code up here, this is the code that you would write if you wanted to solve these equations with this framework. And then the code that's sort of automatically generated is this code over here. So like if you have this code, writing this code is like very formulaic and it's very tedious. And if you do it by hand, it can be error prone. So, if a computer can do it, a computer should do it. And it actually even writes a little more code than this. So like if you look at the functions that are created, there's some that have also these exclamation points here, and these enable a little bit more efficiency. They let you do things in place without having to allocate new arrays. But just to say a little bit more about what this code does. So there's basically 3 functions here. These first 2 functions, this one computes the residuals and this one computes the Jacobian of those equations with respect to H. So like these are the 2 functions you would need if you were just going to like solve the equations. If you just wanted to solve that equation, these are the 2 functions you would need to write. So if you were writing a traditional like solver like FEHM, you would just write these 2 functions. But it also it can compute one more Jacobian. There's another parameter that gets passed in here, and it's for the Q. And so like you can also write the Jacobian for Q. And so if you want to be doing efficient things like inverse analysis, U-cube, and machine learning, you need these other Jacobians. And so like it can automatically write all these Jacobians for you. And so I think that's just looking at like the simplest example you can come up with, but we can also build more complex models. So on the left is sort of a transient Richards equation simulation. In the middle is a wave equation simulation that Sarah Greer, the student at MIT, wrote. She's interested in seismic stuff. And on the right is something I worked on with Dylan Harp. That's a model of an Arctic polygon ice-wedge. But the basic idea is just, you can build much more complex models with this system. And if you think about like a more complex model, so like before, that thing I previously showed was just looking at 3 equations with a structured mesh. If you wanted to write a code for a 3D single phase flow simulator on an unstructured mesh, you would write 19 lines of code. And then the computer would take those 19 lines of code and manipulate them and produce 351 lines of code. So you can see it on the right side of the screen, sort of in the background. This is the code that would get produced. So the code that the computer writes then lets you solve the equations and differentiate them with respect to like the head, the permeability, the boundary conditions, and the specific storage. Yeah, okay, so there's another question. What is the speed up over finite difference? So if you're computing, so the speed up I talked about previously about comparing to finite differences, that if you're doing like finite difference to compute the derivatives, you have to do one model simulation for every parameter to compute the gradient. Whereas if you're doing this, you just have to do 2 model simulations, no matter how many parameters you have. And so, yeah, I mean, basically, you don't want to have to write these 351 lines of code yourself. The computer can do it for you, and it can do it, more reliably and things like that. So if you go to, sort of like the next step up in complexity from just single phase flow, if you solve a 3D Richards equation on an unstructured mesh, again, like the code you have to write doesn't increase at all. It's still 19 lines of code. So the lines are a little more complicated, but it's still 19 lines of code. And then the computer takes those 19 lines of code and transforms it into 483 lines of code. Again, that lets you solve the equations, differentiate them with respect to the head, the permeability, the boundary conditions, specific storage, and in this case, it's Van Newton parameters to characterize the relative permeability. And so now we not only have like a lot more lines, 483, but you can see that this code in the background got a lot wider, sort of indicating that like these 483 lines of code are quite complex. I mean, if you look at them, this is a very long line of code, which at least for me personally, I would never want to write by hand. So, again, like you just want to have the computer doing as much of this for you as possible, and I think pretty much it can do, all this stuff for you. And yeah, just to, I guess to say a little bit more about these models. So this is the model I talked about with Dylan Harp, where it's drainage from an ice wedge. So these are things they model up in the Arctic. So they have like some frozen ground down here, some thawed ground here, and then like pooling water here. And they have these troughs here, or these like little hills, or they're smaller than hills, but little bumps in the ground, and then water sort of flowing in between these high points. And then so there's some questions about like how do these things interact between like the thawing and flow going from like inside this ponded region to the troughs in between these polygons. So anyway, like this is just something we could build in like a day to model this and do model calibration and things like that. So the seismic wave equation, again, this was something that I worked on with my student Sarah Greer, and it's just another example of the types of models that you can build using this framework. And anyway, so seismic wave equation. And I guess just the thing here I want to say is like you can build these models quickly, right? Like it makes it much faster to build models than it traditionally would be, because the things like the Jacobians are being written for you automatically. Even if you only want to do the forward modeling, it makes it easier to write these models. So you can do traditional inverse analysis using these methods. So this is just an example showing a traditional inverse analysis method. So this is some true conductivity field. So this is a hydrology problem. And then the estimated conductivity field. It takes like a few hours to do this inverse analysis on a laptop and the model has a few million parameters. So it's not too small. And yeah, so like, having these adjoint methods really lets us accelerate this process and make it a lot faster. This is some work with Scott Hansen, who he was looking at the value of information that's available from the information that's available when you're doing inverse analysis. And so to do the kind of study that he wanted to do, he needed to solve like lots and lots of different inverse problems. And here, I won't go into the details, but here it was just the key thing here was having these fast gradients and allowed us to solve a lot of inverse problems relatively quickly and sort of get the data we needed to like do this study to look at the value of the information. And again, just most of the things I've been showing are like 2D boxes on a regular grid, but I just wanted to emphasize that like this approach is not limited to that type of thing. So here's showing a discrete fracture network model. So like you can see inside this box here, there's a lot of fractures in this model. There's like a little zoomed in part showing the mesh. So this is like a very complex mesh. The code that we developed, DPFHM, can solve these very quickly. It was about 30 times faster in the benchmarks we did for these DFNs than this code pflowtran. which, you know, is generally considered to be a fast code. And so like the speed up here isn't really due to like any machine learning trickery or anything like that. I think in reality, it's just coming from like using this more, you know, we were just able to like explore better the space of like solvers that we could use. So like the method that they were using to do this in DFN works was this stabilized biconjugate gradient method with an ILU preconditioner. And we found basically better methods. And we found that the best method was Cholesky factorization. And if you're interested in the details, the reference is down at the bottom. All right, so these are all just, so far, like I've been talking about all things you could do sort of like before machine learning came on the scene. And like the point of all those slides is like, now it's just a lot easier to do those things better than we used to do them. So the rest of the talk is going to be more focused on like combining these ideas of having like differentiable physics simulators with machine learning tools to sort of see, you know, what new things we can do. And so the next thing is going to be about, you know, basically trying to look at, can we combine physics models with machine learning models to do better than traditional inverse methods? So if we're doing inverse modeling, can we use these machine learning ideas to do things better than we have traditionally done? So there's multiple ways to like attack this problem. And sort of just at a high level, I would say like there's two basic approaches. One is you have a machine learning model and physics training data and observed data. And basically what you're doing is you're training the machine learning model to just directly map from the observed data to like the inverse result. So like if, for instance, you would just be, you know, like the way you would set up the training data is you would run a bunch of forward simulations, like mapping permeability to pressure. And then the machine learning model would just be trained to go the other way. So you would just be training the machine learning model to take some pressures and go back to the permeability. And so like the advantage of this is that it has a very low marginal cost. So like if you want to do one more inverse analysis, you just need to run the machine learning model one time, and that's extremely fast. The downside is that it has a high upfront cost. So like generating the training data is very expensive. And you know, in some cases, it can be more expensive than just doing the inverse analysis in the first place. So like there's places where that's useful, like for instance, if you want to do things in real time, which I think is relevant for SMART. Another approach that I'm going to talk more about today, and so I guess if you're interested in sort of this more machine learning based approach, you can look down here in the reference in the lower right corner. There we have, you know, there's a lot of methods for doing that, but this is one that we developed. But today in this talk, I'm going to talk more about a different approach where you combine a machine learning model and a physics model with observed data. So in the previous approach, we just had sort of physics training data, but now we're actually like combining the machine learning model with the physics model to do the inverse analysis. And so the advantage of this is that it has a low upfront cost. Like the cost of generating the training data for the machine learning model is much lower, but it has a higher marginal cost. So every time you want to do one more inverse analysis, it's more expensive than with the other approach. And so the basic approach that we're going to talk about here is based on a variational autoencoder. So you generate some images of like what you think the subsurface looks like. You would train a variational autoencoder to like, you know, map these images to a latent space and then map them back to this high dimensional space that it looks like, where it looks like a permeability map. And then once you sort of are happy with the way that this thing has been trained, then you take that model and you combine it with the physics model and you actually do the inverse analysis. So you actually do the inverse analysis like in the latent space. So the way you sort of construct your loss function is you map from the latent space to the decoder, and then that goes to the physics model, or sorry, that produces like a permeability map, which then goes into the physics model. You compare that with your data, and then you just do some traditional gradient-based optimization process. And so like within the context of that idea, we're going to be comparing using dense, shallow neural networks versus deep convolutional neural networks. And it's a little bit of like a David and Goliath story where like generally like these deep convolutional neural networks are much more powerful than the shallow dense networks. But in this case, there's actually some advantages to using the shallow dense networks. And we're going to look at two different types of permeability fields. So one is on the left, just like the traditional multivariate Gaussian field that's commonly used in hydrology. And then on the right, it's going to be a permeability field that has a bimodal distribution. So like there's these red regions that are high permeability, and then there's these blue regions that are low permeability, and there, you know, then there's some variability within each of these regions. And so just for completeness, to compare with the traditional geostatistical approach, on the left this is what you would get for the traditional geostatistical approach, which is like the most commonly used method in hydrology. And then on the right, this is showing what you can get with this sort of variational autoencoder, this machine learning approach that we're talking about. So, I guess the takeaway here is like this at least beats like the baseline of traditional inverse methods. And what we found is that if you use like a deep convolutional network, you can sometimes run into problems. So like sometimes the results are good. Like you can see this result is good, this result is good, this result here on the right is good, but this result, this sort of third result is actually quite bad. And this sort of seems to be something that creeps up as the power of like the neural network increases and the neural network becomes more powerful. You seem to start to see these problems more frequently. And I just want to emphasize that so these results aren't like a bug in our code. Like independent groups who are also looking at these types of methods are also seeing the same thing when they use these deep convolutional networks. But if we use the shallow dense network, we're much less vulnerable to those problems, and it sort of tends to work well. At least for the problems that we studied, it seemed to work well in all instances. So in this case, the shallow dense network is sort of outperforming this deep convolutional network. And we sort of think that there's a trade-off between the accuracy of the reconstruction and the feasibility of the inverse model. So like as your neural network becomes better at representing like your permeability maps, it also makes it harder to like solve the inverse problem, or like to get to the global optimum for the inverse problem. So like the dense shallow network is kind of in a sweet spot where it's not super accurate with the reconstructions, but it avoids the problems with the sort of making the inverse problem infeasible. And so like the thing that's good is that at least the dense shallow network still provides enough accuracy to outperform existing methods like the principal component geostatistical approach. All right, so now transitioning to like a problem that's more closely related to smart stuff, like related to geologic carbon sequestration. So I'm sure everybody here already knows all this stuff, but there's too much carbon dioxide in the atmosphere, and this is problematic for the climate. And so one of the best candidates for dealing with this is injecting carbon dioxide into the Earth's subsurface. But then, of course, there's various problems with that. For instance, if you inject too much carbon into the subsurface, you can overpressurize it and cause problems like induced seismicity, or you could like fracture a caprock or something like that. So, you have to manage the pressures in the subsurface in order to avoid these problems. And so there are some of the key characteristics of decision support for sequestration, I think, are that there's lots of uncertainty in the properties of the subsurface, which makes it hard to know how the reservoir is going to react to injection. And so we were looking at this question of, can we develop a real-time tool to help make decisions about how to manage pressures in the reservoir? And so we're combining these machine learning and physics models and showing that we can sort of develop such a tool. And I think especially like in the context of CO2 sequestration, I think having this combination of machine learning and physics models is really powerful because, for instance, if you compare it to like oil and gas, where there's, people have been doing oil and gas for decades. And, if you look at hydraulic fracturing, there's like tens of thousands of wells that have been operated. But CO2 sequestration is much more data poor. We don't have as much experience. So having these physics models in the loop, I think brings a lot to the table. And so this is showing some results for training a machine learning model to manage the pressures in the subsurface. So like if what's basically going on here is you're injecting some fluid at this point, you have a critical location down here and you're extracting fluid here. And the question is, you're basically in this setup, you're injecting a fixed amount of fluid. And the question that the machine learning model is trying to answer is like, how much fluid needs to be extracted in order to make sure that the pressure at this critical location, does not exceed some critical threshold. And here we have a workflow that you can see on the right. So here, like things like the transmissivity and sortativity are being passed into the neural network. The neural network is producing extraction rates as an output. This goes into an automatically differentiable physics model, and in this case, it's a really simple model. It's like an analytical model, and then we have this loss function, and we can just train this And as we're training it, we're just computing the gradient, doing some gradient descent-based method, tweaking the weights of the neural network until we eventually learn how to manage the pressure in the reservoir by controlling the extraction rate. And so we can do this for multiple wells in multiple locations with multiple critical locations. And I think somewhat interestingly, it actually worked better in this case. So if you look at like the overpressurization error, so this is showing it for the single injection, the case where there's one injector, one extractor, one critical location. This is showing it for multiple injection, extraction, and critical locations. And so like the error in the overpressure is actually a little lower in this case. And sort of my hypothesis for why that is that the machine learning model sort of has more degrees of freedom that it can play with to manage the pressures in the subsurface, and it seems to do a better job. So that was all for a very simple model where it was analytical. As earlier in the talk, you saw that we sort of have complex numerical models that we can insert in these workflows. So this slide is about putting in a more complex model. So now it's not an analytical model, it is a numerical model. And so instead of having like a homogeneous porous medium to deal with, now we have heterogeneity, and we can basically do the same workflow, but now with this more complex model in there, and it still basically works. We get a little bit less accuracy in how accurately we can control the overpressures at the critical location, but it's still quite small. It's something like 10 to the minus 3 megapascals, which I think is generally quite small. And so yeah, this is just showing the training process. This is showing the way you might actually use this in practice would be like, of course, the input to these models is going to be like a heterogeneous permeability field. And of course, like we're never going to know like exactly what that permeability field is, but we might have like an ensemble of possible permeability fields that are consistent with our understanding of the subsurface in that area. And so then if you had like, say, 1,000 of those, you could run all of those through this machine learning model to get like what the extraction rate should be. And then you would get a distribution like this that shows what the extraction rate should be. And in this case, if you were probably making a decision, maybe you'd say like, oh, we're going to do like I don't know, you'd come up with some maybe confidence level to say like, we want to be sure that in 95% of these cases, we're going to be extracting enough fluid. And then so you might just pick a point like somewhere around here to say like, we're going to do this extraction rate. That's going to keep us safe for all these cases. And yeah, so there was a question. So I guess this was, maybe I missed this question earlier, but it says, at which degrees should we train the decoder ML in order to receive gradients from physical components? Should we do these two components together or pre-train an ML decoder? So I'm not 100% sure I understand the question, but going, I guess, back to like this slide, I mean, we're doing the training of the encoder and decoder offline before we start doing inverse analysis, which I guess if that doesn't answer the question, maybe we can follow up later. And I went too far. Yeah, but anyway, that's pretty much what I had to say. So just to wrap things up, so I think differentiable programming is good for a number of things. Like one thing is it's good for rapidly developing physics models. And I showed some examples of that. And this is just something I'm interested in. So like if you're interested in some physics that you would like to see implemented in this framework, like I would be really happy to help. So feel free to reach out to me. My email address is there. Another thing it's good for is accelerating traditional scientific computing workflows like inverse modeling and uncertainty quantification. So we looked at examples of inverse modeling using a combination of the physics model and a variational autoencoder. And something that was kind of surprising here was that we found some advantages to the simpler, shallow networks rather than the deep networks. And we also showed some examples just using traditional methods like the geostatistical approach. And it's also good for training machine learning models with the physics model in loop. And I think this is like especially good when you have limited data and limited experience, like in CO2 sequestration. So here we looked at training a machine learning model with a numerical subsurface flow simulation and the loss function, and we showed that we could use that to help manage pressures in the subsurface. And with that, I'm happy to take any questions. Thank you.
Thank you, Dan. These questions in the chat have been fantastic, and we encourage our guests to keep asking in the chat, or if you want to unmute, you can ask live.
Yeah, thanks, Dan. So that was a very interesting talk. And like we typically do, if you want to ask questions, please unmute yourself and use the hand button so that Mia can identify you and then call upon the individuals who are interested in asking questions. I know Jyoti has his hand up, but I would like to sneak in sort of a philosophical question.
Mm-hmm.
And so, Dan, it seems to me that with differentiable programming, you're accelerating even traditional physics-based computational workflows. So as our computing power increases, and we use more and more GPUs, things like DP, and also better solvers, would we get to the point where a full physics simulation that takes hours today might take minutes, and so the need for building machine learning proxies keeps going away?
I don't know. I mean, I would guess probably not. Like, I think the speed ups, like for instance, I showed the speed up compared to like p-Floatran by 30x. Like I think that's kind of like getting somewhat close to the limits of what we could realistically hope to do. Maybe like we could get another like 3x or something like that over what I have. Because I was using CPUs to do that. I think maybe with GPUs you might be able to get like another 3x. And the other thing is like in terms of the physics models, it's sort of like as the computational power goes up, the expectations for like how many nodes are going to be in your mesh go up too. Like I think in the subsurface, we just always have this problem of like, heterogeneity is there at very small scales. And, when we have like reservoir scale models, like we're never resolving that. So like, I think just as the computational power goes up, we're just going to want more out of our numerical models.
Okay, thanks. Yeah, over to you, Mia, and then probably Jyoti wants to take the first shot.
Jyoti, please unmute.
All right, can you hear me?
Yeah.
Okay. Thanks, Dan, for the nice talk. So I just wanted to clarify my earlier question regarding speed up over finite differences. We understand that you need two, let's say, simulations to compute the gradients everywhere, and that's the power of the adjoint state method, not necessarily what is that, differentiable programming. The adjoint state method lets you do that.
The power of the differentiable programming with respect to adjoint methods is just that it makes it much easier to use the adjoint methods, right? Like it used to be like you had to work very hard to write all the code you needed to write to like implement these adjoint methods. And, anytime you wanted to like differentiate with respect to a new parameter, you'd have to write like a new Jacobian. But like, so like the idea for differentiable programming is just that it makes it much easier. Like it just writes all the Jacobians you need right at the beginning. And so like that makes it easier. And so, yeah, I think, can I see if I understand your question about the finite differencing? So like there's two sort of finite differencing things, right? One is like you have a loss function and you're computing finite differencing to compute the gradient, right? And that's where like differentiable programming and adjoint methods give a huge speed up over that.
Right.
And then there's finite differencing to like implement the simulator, right?
Right. That's what I was asking about. Yeah.
Yeah, so differentiable programming doesn't give any speed up over that. Like basically differentiable programming just lets you like implement that finite difference simulator in such a way that it makes it very easy to use the adjoint method.
Okay. That was my confusion, because when you showed seismic simulations done with differential programming, so it was not clear to me that how would differential programming help you there. So is it fair to say that the software that you're talking about is similar to what like others have written, like AutoGrad and JAX?
Yeah, I mean, it's similar. So like the niche that's like a little different than what is traditionally done in those things is like dealing with sparsity,
Okay.
which like those frameworks are starting to have some support for sparse matrices. So like if you're doing these scientific simulators, you know, having sparse matrices is like essential. You know, like you really, you know, having sparse matrices in your simulators is like table stakes to have like a simulator that's going to give like performance that's not complete garbage. So like I think those frameworks, I can't remember what it was. I think JAX has like some experimental support for sparsity. But anyway, like I think those ideas are starting to get picked up in the more traditional machine learning frameworks, where like, you know, for the stuff that they were doing, it wasn't super important, but for scientific computing, it's like really essential.
Okay, great. Thank you.
On cue.
Yep. Hey, Dan. Yeah, nice presentation. And I have some couple questions, mostly kind of simple question, but and so when you're showing some of examples, in particular differential the programming, and probably you know best still kind of solver is iterative solver at this moment, right? And they really struggle without proper preconditioning because of some different probably either precision or some data
because the condition
types,
numbers.
right? Yeah, when
Yeah.
you're really dealing with multi-physics problem, in particular like flow mechanics, we have some different kind of scale response. We need to do a lot of those preconditioning to make some metrics solvable. So how about the differential programming? Do you still need to do something like preconditioning?
Yeah. I mean, you know, differentiable programming is basically doing the same thing that a traditional simulator is doing. It's just sort of making it easier to implement that simulator and making it easier to incorporate in like a machine learning workflow.
Mm-hmm.
So like, you know, my code DPFEHM is like, you know, using the same numerical methods as FEHM. It's solving the same equations. You know, it's basically doing the same thing. It's just that it's, you know, easier to develop DPFEHM than FEHM, and it's easier to integrate DPFEHM in with the machine learning frameworks.
Yep. Another question is, you showed Richard equation. That's really nice. And since you are kind of start handling some nonlinear problems, how about typical kind of heterogeneous field like multi-phase flow, right? You need to update all those actually parameter values every time step, and how easily actually we can implement those in a differential programming framework. Was some
Yeah, I mean, you know, like the Richards thing is also updating the permeability at every time step.
Yep.
You know, like I don't see that as like a limitation. And we have some more general like multi-phase code that's still sort of, you know, it's passing some basic tests like, you know, Buckley-Leverett problem and things like that, but still needs more work before it's ready for prime time. But you know, like I think you can do that. I don't think there's any fundamental issue.
Okay. Yep. Thanks. And last question is about actually variation autoencoder. It's really great to see actually you evaluate those shallow versus deep architectures. We did some different ways, but I really, you know, we kind of struggled to actually generate really nice map for the some bimodal type distribution. That's why I mean that may be caused by our kind of CNN architectures. Probably it's not really huge deep, but any and this kind of deep CNN architectures. And so instead, actually, we're looking at more kind of GAN style. So GAN has ability to generate those type better. But obviously, if variation autoencoder will work, I think it's much easier to work with variation autoencoder. So that's really a nice examples. I will follow up on that. We during actually phase one activity, we did some data simulation framework using variation autoencoder through those latent space update when you're done, but we also use some folder model developed based on data-driven model so that we can speed up quite dramatically. but that's kind of where actually we can discuss a little bit more how to implement during phase 2 activities. Okay.
Yeah, sounds good.
Mm-hmm.
Yeah, and yeah, I think basically any generative model could be plugged into that basic concept. I haven't tried it yet, but I'm interested in looking at like deep generative flows to see if they can be good there. And then I see there's a question from Dan Liu in the chat, who's asking about, he says, you mentioned using the ML model to solve inverse model directly, that is, learn the observation parameter mapping, but based on my understanding, neural network is for function approximation. And it says in the subsurface, our inverse problems usually suffer from ill-posedness. I'm wondering how to use neural network to solve the inverse model directly. Thanks. Yeah, that's a good question, Dan, and also very good name. But so the basic idea is like when people are setting up these models that do the inverse mapping directly, kind of the way they get around the ill-posedness is that when they generate the training data, the images have like a certain structure that's representative of the subsurface. So like, if, for instance, if you looked in that reference that I gave that, Mean is the main author on, who just posted in the chat, there's like different types of permeability fields, for example, like ones that have high permeability channels. And so like, for instance, you might just train the neural network only on images that are like these high permeability channels. And so it sort of has like this built-in regularization in it that like, the output is going to be looking something like the training data. And so like there's this regularization effect that's sort of embedded in these neural networks that directly do the inverse modeling.
All right, with that, we'll call it a wrap. So thanks, Dan, once again for a very interesting talk. And thanks to all of you for being here and being part of this Smart Webinar series. And we'll see you next time. Thanks, Mia.
Thank you, everyone.
Everyone.
Thanks, Dan.